everybody, and thanks for the opportunity. It's great to be here. It's been fantastic watching, the rising stars in the field as well as, the other speakers. The first talk after lunch is always a little bit difficult. This is going to be, I'm going to try to show as many pictures and videos as I can, and hopefully try to tell you a little bit about air transportation systems, and in particular, what I think are some of the opportunities for us to actually use data science to build smarter air transportation systems, which I will admit, I am in an aerospace engineering department, but it's also something that I think everybody likes to complain about, but nobody really thinks about what to do about it. So I'm going to try to tell you all about it today. OK. So I'm going to start with a lot of things on how things used to be pre-pandemic. There's been about, the Wright brothers flew in 1903, right? So it's been more than a century of flight. But over time, and especially in the past 50 years or so, arguably, air transportation really has become a driver of global travel and commerce. In terms of value, most things don't get transported, most freight doesn't get transported by air in terms of volume, but in terms of value, it does, right? So if something is perishable or time sensitive or of extreme value, you're more likely to send it by air. But as this demand has grown, already there's a fair amount of demand in terms of passenger enplanements. So the way they measure demand in the industry is to say, OK, how many people, not individual, separate people, but how many people roughly get on board a flight and start a journey every year? And that's about 4.6 billion people. And back in 2019, there were about 51 million flights per year. And the flights are pretty full. So the average load factor is how full is your flight. On average, back then, it was about like over 80%. Usually, load factors of that size mean that there's a lot of flights that are completely full. And why does this matter? Well, if there's a delay or a cancellation and you want to get on board the next flight, the odds are that you're going to have to wait a really long time to get on your next flight. There is a real impact of just these delays, right, that happen in the system. There's an environmental impact. There's a lot of issues with the environmental impact of aviation. As an absolute volume of amount of greenhouse gas emissions, it may be a fairly small fraction of all human contribution, but a lot of this fuel is being burnt at closer to at high altitudes. And so the impact of it does tend to be a little bit higher than if you were actually doing it on the ground. And then the second problem is that a lot of the delays sometimes are on the ground, and that's a problem as well because you design the engines to be really efficient at high altitudes and not necessarily on the ground. So there are these weird phenomena that go on. What has been happening, though, and this is really where data science can come in, is everybody's realized that you can't keep business as usual. And so there have been, for almost the past 20 years or so, this move to build next generation air transportation systems, right? Like change the way the system operates. And the key drivers of this have been autonomy and automation. So, and that's really where, if you think about it, a lot of the decisions used to be made by humans, and they were manual processes. And can we move it to provide decision support to people who are making this, who are actually driving or flying the system, and then autonomy as well. So just like we've seen the revolution in self-driving cars, there has been a push to what are called drones and what used to be called urban air mobility, but really is now called more advanced air mobility because it may not be only in the cities, right? You can think about a lot of the use cases, the compelling use cases, are in fact going to be in more hard-to-reach areas or areas where the roads, you have a disaster and your road infrastructure, your ground infrastructure is disrupted, you can still fly. And so you can, if you have the right aircraft, you can fly there. And so, but that change into trying to build, increased autonomy, which is more intelligent aircraft, and increased automation in terms of how we operate it, really is what gives the opportunity for data science and computer science techniques here. And then in terms of good news, I said this was pre-pandemic. We are back in terms of demand. So if anybody has flown recently, you'll know, you'll probably have a new horror story. And the other issue that's happened now is that a lot of the workforce actually got shifted, and people left the workforce in aviation over the pandemic, and they haven't been hired back. So now you have the passengers back, and so we are seeing a lot more in the news where when something happens, there's days, if not weeks, of disruptions because because the processes used to be human, it was basically institutional knowledge that was in somebody's head that used to be used to make those decisions. And now when there's a problem, nobody knows what to do because the person who did it has moved on to something else, to do something else. But again, that is an opportunity for all of us. So I did say, probably the big revolution, the biggest interest right now, and it is hard to tell how much of it is hype and how much of it is reality, will be reality, is this idea of advanced air mobility. And this is a vision that we can all get behind, right? So this is an artist rendition from NASA. You have these cities, and we all have, just like we have our rideshare services now, it'll be those, but in the air, and we'll never have to wait in traffic. As an aerospace engineer, I have to say that every single person I would talk to who was not in an aero department would ask me, where's my Jetsons moment? Where's my flying car? And I think we're still saying your flying car is coming, right? Except it's a lot closer. And so the question is, how do we do this, right? Like, how do we enable this? Because there's a lot of interest in getting here. And there's a lot of private investment now in this space. So I just wanted to show, drones we're using very generally as any autonomous aircraft, right? Or any aircraft which does not have a pilot on board, a human pilot on board, are called drones. So these dark blue bars are general drone companies' investments. The slightly lighter blue bars out there are in passenger drone companies, so like air taxi services. The thing that I should point out is the almost non-existent gray bars there are on how these drones are actually going to, the system-level problems on these drones. So there's a lot of money in building the autonomous cars. There's almost very little research or very little investment that's going into actually people thinking about how will these cars actually, what's the road going to look like, right? To use that analogy. And so this is what I meant by there's a lot of interest and hype here, but it's also important for us to understand as on the research side that if we don't figure out how they're all going to operate collectively, these investments are going to be just, you have a bunch of new aircraft, right? And they're not going to go very well. The main trend is not dissimilar to what we see in the automobile industry, where these tend to be, what are called eVTOLs, which is electrically powered vertical takeoff and landing aircraft. The idea being, unlike the fixed-wing aircraft that we have, which would require an airport or a landing strip, you actually have something that looks more like a helicopter that can take off and land without needing all that, that much space, and you don't want to be using fossil fuels. So the shift to actually moving to electrically powered vehicles. So that's a fairly similar trend, and with autonomy, right? So there is a clear parallel to what we are seeing in other modes of transport as well. The point that's worth thinking about is this idea of autonomy, right? Like that the aircraft is going to do something on its own is not a new one, right? Like we think about, we now have machine learning, and we can build autonomy and we can do it. So it's worth thinking about. This picture on your left is the first flight, Wright brothers. As I said, that was 1903. The picture on the right is the inventor of the autopilot, Lawrence Perry, at an air show in France in 1914. And it's quite interesting because he had his mechanics step out onto the wing so that people watching could tell that he didn't have his hand, there were no hands on the controls, and he has his hands too, right up there. Look, ma, no hands, and flying in a demo. So we say, okay, but this is, short periods of time having something go. What about longer duration flight? Well, that is a real New York Times headline from 1947. Right? That's 75 years ago, of the first robot-piloted plane that crossed the Atlantic. So went from Canada to the British Isles. No hands-on control. Takeoff, flight, and landing are fully automatic. I actually highly recommend this. You can go back and see the archives and read this article. There were civilian observers on board this aircraft. And when they say a robot-piloted plane, it is a mechanical brain, right? This is 1947. And if you think about what people thought we would use an aircraft like this for, it was, of course, there would be wartime applications, but hey, package delivery, which is the thing that we're talking about now, right? Like when Amazon Prime says we're going to deliver a package in your backyard, it's going to be an autonomous drone that's dropping it. 75 years ago, people said this is going to happen because we had the technology. What has not happened is, and what, again, if we think about methods from machine learning and data science that can do, is do this in a way where you're not shutting down everything, shutting down all the airspace. Everybody moves out of the way and you fly a single thing. Actually have that ability to do it collectively. And again, if we think about it, this is a challenge in much of autonomy when we think about designing it. It is not the problem of having a single car go down an empty street to the end of the street. It is, what do you do if you don't have a street? Or what do you do if there are multiple cars? And what do you do if there are human beings? So adapting to the environment. And that's where you actually need ways of both collecting data, observing it, and bringing it back. And the reality of these systems is at some level, there are going to be human beings involved no matter what. There might be other vehicles that are piloted by humans. There's certainly going to be, at some level, the ultimate, the people who would like, these drones are providing services to, are going to be human beings, right? So ultimately, there is some human, I would like to do this task. I would like to go to this place, and that is going to be the driver. And so we actually need to understand how a lot of those incentives and how a lot of that behavior works as well. So, this is just summarizing all of that, and this is Airbus. Like, everybody has a picture of, what are these, the urban air mobility is going to look like, and what has changed really is, not just the vision of what these aircraft are going to do, but also, what these aircraft are going to look like. As I said, largely autonomous, largely electrically powered, and at a range of different sizes, right? You could have small package delivery. You could have, people, any number of things going on here. And at scales that we have not actually seen before. So if we think about the projections, why have the investments in these aircraft been at the scales, the levels that we are seeing? Because if you look at the demand projections, who knows, right? It is a projection. But this Airbus study says they expect that by 2035, which is not that far away, there's going to be 20,000 flights per hour over Paris. There are currently about 100 flights per hour over Paris. So, you're thinking about, okay, we think we're going to have those orders of magnitude more flights. You need to understand, okay, how are these actually going to interact with each other? Because the idea that I'm going to shut down the airspace every time one of these has to fly is not going to be viable if you're thinking about those scales. And then it's sort of similar projections in the US as well, especially when you think about these smaller scale drones and the things that they might do. So I sort of want to summarize what I think are some of the challenges, and then I'll show some other, very quick things on potential opportunities. So the first, as I said, is really unprecedented numbers, the scale of operations. And so a reasonable question to ask is, how does the system operate somewhat efficiently at these scales? The second set of challenges that actually make it different from what aviation has seen before is that it is a new competitive landscape as well. Because we're used to the aviation system having either the FAA or Eurocontrol. So there is someone who's managing all the traffic. The airlines are there. But the airlines are mostly flying very similar. They want to do similar things, right? They have aircraft that they want to fly. They have passengers. They're doing this. Whereas now you could have somebody who's got flying people, someone who's flying little packages, someone who's flying larger packages, someone who's doing photography for real estate, someone who is trying to ship organs for an ambulance, and they all, it's different kinds of competition from what we're used to dealing with, and it's a much more competitive environment, if you think about it, than the traditional aviation environment. And that has actually already seen some issues come up. So privacy, which didn't really used to be, airlines, you publish your schedule 6 months in advance, right? Everybody knows you're flying a flight, and that's never been an issue. But imagine having rideshare companies or companies that are actually competing saying, you need to tell us who you're picking up from where, 6 months in advance, or let alone a day in advance, right? Like there's clear competitive advantages to not sharing information. And that's information that if you think about efficiency and trying to make sense of how we manage this, you need that information. And so now there's a whole set of questions on how do we actually give some guarantees of privacy of that information, but at the same time incentivize the kind of information sharing that you would need to get better system performance. And the third thing is fairness now becomes an issue as well, where very often there are concerns that there are all these different players who want to operate in this market, and the moment one moves in and you say, I'm going to shut down the airspace for everybody else, that's a monopoly. And so you really want to do this where everybody has access and there's equitable access. We don't have answers to these, right? These are all open questions, but I think it's, again, an opportunity to now think about how do you build algorithms to deal with this. So I'm going to talk about two things. I promised movies, so I'll start with the movie. This is sort of explaining, shows how the system operates currently. This is a day where there's weather in the New York area. So this is roughly the east coast of the US. That's New York. These are storm weather cells that we're all used to seeing. The red dots are aircraft, the location of an aircraft, and the white line is like the 5-minute history of that. So one thing we see is, because there isn't enough actual planning and the system is very reactive, as a storm moves in, you start having these holding patterns where the delays are propagating, and you can actually, well, wait. Sorry, I wanted to. If you noticed, you could have holding patterns pretty much forming 800 miles away in the Midwest, because there's a storm center, the storm system that's pretty localized here, right? And but what that also gives us as people who build solutions is opportunity for both analysis and optimization. So the kind of questions you can ask. Well, from a system perspective, how do we know when the system's actually doing well under those conditions? How do we predict how the system's going to behave? This is very complicated. And then the optimization piece, which is how do we actually make use of this and not have this sort of responsive thing where I don't know what's going to happen. I don't really predict what's going to happen, and so I wait till it happens, and then I respond, and then the system has really bad performance. And the key challenge here very often to the way we think about things is the system is very connected. So local events have very far-reaching impacts. So this is just 3 examples where from a few years ago, but this is a repeated story where you could have a power outage in Atlanta, or a fire in the Chicago Air Traffic Control Center, or even weather impacts, and these things spread through the entire system. This sort of power outage. So this was a fire in a router room in Delta operations. The fire itself was put out in 45 minutes. The impact of it lasted days and was like $170 million, right? So it's one of those things where once you lose control over what's going on and you can't predict it, it just cascades, and then you don't have a plan for recovery. And again, where you can do is you have to look beyond. I mean, like in many of the problems that we've seen today, you have to look beyond that local impact, right? Like things can look very similar. And in aviation in the US, people will say the New York City is the center of the world. But the reality is things can look, if you take 4 days when the weather in New York looks really similar, people will ask, why is the system behaving differently across these 4 days? And the answer is, well, the rest of the country looks quite different, and it matters what the demand is. It matters, you can have really bad weather in New York, but this is the Saturday after Labor Day weekend. Or, yeah, Labor Day in 2014 was the September 1st. So there's nobody flying. So, if you're really going to have bad weather, that's the day to have it, right? It's not going to impact very many people. So what we can do and what we've done is working with a major US carrier, actually build these tools, right? Use essentially the data, operational data, to start saying things like, okay, how are you doing? If you change your schedules around here, what does it do? And so get a sense of that problem of just benchmarking your performance, things that work, things that don't work, and then run what-if scenarios to predict what's going to go on, right? The second piece of it is really the optimization piece. And this is a large-scale optimization problem where, again, the problem is that connectivity. And the connectivity is because in the US, only 6% of aircraft fly only once a day. Most aircraft, are going to go from, airport A to airport B to airport C. And if you now say, I'm going to look locally at the weather now in airport A and decide what I'm going to do without looking at which flights are doing what, you're going to end up possibly canceling the wrong flight, right? Like you have, in order to prioritize, you actually have to take into account the things that you're going to do later. And it turns out, and this is very consistent with both US data and European data, about 40% of delayed flights are not delayed because there's weather at either the origin or the destination. They're delayed because the aircraft showed up late, right? And so it's just purely that propagation piece that does not get accounted for. And this problem of trying to model this, and I'm not going to go into the details, is something that, again, from the late 80s has been done. What we can do now is if we have those prediction pieces, we can actually solve very large-scale problems. So problems with projected demand for manned aircraft, unmanned aircraft, and everything else. And I'm just going to show you a video of what that looks like. They're very crowded skies, right, in these projected things. But you can solve them, right, in a matter of minutes. It requires the prediction, and it requires being able to parallelize and distribute your computation. But those are things we can do, and these are incredibly crowded skies. The red aircraft are the unmanned aircraft. The blue aircraft are manned aircraft. They're doing all sorts of things. There are projections that you're going to have, aquaculture, like expeditions where people are spotting things, which you need to do. So along those lines, the last thing I wanted to sort of talk about, and just in a couple of minutes, is the question of fairness. And the fairness comes up in different ways. One level of fairness has a parallel with ride-sharing systems, right? Destination discrimination, where, again, if you have air taxi services, you actually do want to make sure that they're serving all neighborhoods equally. And there's that sort of multiplexing where you want to be efficient, but you want to be efficient in a way where you're actually also serving all competing demands on this. The other sort of methodologically same problem, but a different application that's more on drones I wanted to talk about is this issue of actually multiplexing on board a drone. Because we do want these services. If I have a platform and I'm flying these drones, I want to be doing as much as I can there. So the example would be, like, and then the kind of thing that we would build is, let's suppose I have 5 drones. These things have very limited, these small drones that you can buy off the shelf have limited battery life. And you have 5 things that you want to do. Different people want to do different things. Someone wants to monitor traffic, right? Right now, most traffic details are essentially there's a long lead time. Whereas you can fly a drone, you can get those measurements very quickly. You want to see if there are parking spots around Cambridge. In order to fly these, you actually need cellular connectivity, so you need to know how good your cellular connectivity is. Air quality measurements, right? Yeah, there are reasons why it's a good way to go and sample air quality. What you want to do in infrastructure things, and you don't want to be flying different drones to do each of these because it's leading to an inefficient problem and hard scaling problem. So what we can do and what we've done is actually build algorithms where if you have these different tasks where some things you want to keep continuously monitoring, some you want to come back every 10 minutes and see what the state of things is. But while I'm doing that on my way, I could be doing something else like measuring my cellular output, or if you have these air quality models that and every one of these has its underlying, there is a problem there as well, right, in terms of data science on how do I know where I want to go and measure my air quality, sense that, tell my drone, and then the drone decides based on these different things what to do and so on. But what we can show is that you can actually come up with algorithms where you don't sacrifice efficiency very much, but you can actually manage to multiplex in a way where you can serve throughput. So that is, broadly the set of things that I wanted to talk about. But as I said, I think this is an incredible opportunity because it is clear that there is interest and there is demand for this, right? So if you think about inspection of infrastructure and whether it's pipeline infrastructure, inspections in, along or, of the oil and gas infrastructure or railroads, or if it is, reaching medicines to faraway places or, quick response in urban areas. There's a lot of things we would like to do with these drones. But we need, in order to do it in a way where it's efficient and, and you need that efficiency for it to be practical. You need the equitable access in order to actually have this going. And it has to be sustainable, both in the sustainability in terms of power consumption and in the way where it's an economically sustainable system. Because right now, there's a lot of capital investment that's happening, but you ultimately need to have a business model which actually can keep the system sustained with revenue. And you want to do this for really, literally, I think the sky is the limit here, right? And so that's the set of challenges that we have. So thank you, and I'm happy to answer any questions.
I just wanted to know, what kind of models are used in that? Are those dependent on, related to machine learning models? Or if yes, then how do we add those constraints in the machine learning models and implement it?
Okay, so that's a great question. So the ones that I showed are really more traditional optimization, they're mathematical programming models, right? We're solving them as really large-scale integer programs. But as you think about drones, and this is work that we're doing, it is very clear that the drones themselves, we have a fleet of drones. The more logical thing is that they're going to have, they're going to self-organize. It's not going to be centralized optimization. It's going to be, essentially RL-based or something like that, right? So I think a challenge that we have some understanding of, but an open question is how do you actually, bridge that scale where one part of the system runs using centralized optimization models, which requires certain types of guarantees on performance. And then you have another part of the system where the vehicles are operating using, more learning-based models. And how do you take the kind of performance guarantees you get from a learning-based model for vehicle performance and translate that to something that, a traditional optimization model can use? That's a great question. I think we've made more progress in the individual pieces than actually that interface.
Thank you. Great talk. One question that I have was about this Mobius platform that you're talking about. How easy do you think it would be to convince these private stakeholders to install these sensors or extra things that would basically affect their performance. I mean, they can argue that, I mean, you can install this on a Boeing 777 and monitor whatever you want to monitor through that. Why should we affect our performance and share that data that we can be selling instead of just sharing it for free, right? So how do you think that would play out?
So I think there is one of the things that we're sort of we think is an open area is building a marketplace where if I own, let's say, these things can be done with a toy drone, right? Like not toy drone, but a drone that I use for other things. If I'm not using it for that, or I'm doing it anyway, if you actually build a marketplace here, if you tell me I can make some money while I'm doing something else and I'm not using it, I could also be picking up these additional things. You'd want it. So I think for a lot of these things, because the demand for some of these things, if I actually have enough demand where I'm not going to be doing anything else and it's going to be with that, most private people, operators are not going to share. But there's a lot of benefit to actually having a platform where I can say, I would love to say, I'll set mine out. I have a platform. They're going to take it. If they're going to use it, they're going to give me money for how much they've used it, right? So I think the idea would be more building that layer of incentives and a marketplace where I can make money on the side if I'm not using my drone.
Thank you. I have a question on sustainability side. So I think you covered a lot more about traffic and other things and issues that we have currently. But all these competitors, how are they taking into account of sustainability?
So on the aircraft, so the thing that I did not touch on, you're right, is the aircraft sustainability side. And certainly aircraft manufacturers and aircraft operators, airlines care, right? I mean, fuel at a minimum, they want to reduce fuel burn, and so they have operational things there. There is an entire, there's two sets of things that I think there are opportunities for data science to play here. One is in understanding operational performance versus what is certified. Because, I mean, as we all know, when we buy a car, there's some miles per gallon that's given there, but there is a difference between what actually ends up, what my car gives me and what it's supposed to give me. So I think there, again, those predictive things will help an air carrier do that much better. There is also a huge opportunity on any regulator side to know what that variability is. And that, again, there's that piece of data science where we've done more work. Both of those are extremely challenging because there is almost no incentive to share information, right? So, I mean, I would, but if you think about research outside the operator, the operator will put a lot of funding into data science techniques to get better performance, but they're going to be a little bit more hesitant to tell the regulator or share that information, right? I mean, there's clear reasons why the incentives are not aligned there. So that's sort of one place where there's opportunities. There's also a lot of opportunity on predictive maintenance, right? So this is entirely, I talked about system level performance, but I did not talk about what you can do, the problems and challenges in improving sustainability or improving any measure of performance at the vehicle level, where if I actually knew that it was doing, and there you can imagine there's a huge wealth of machine learning problems there, right? Like any other complex system.
I just have one following question to that. I mean, if this is in the process, trying to build these kind of vehicles, as they're working on this, are they thinking of sustainability? Because you did mention that there is not a lot of investment in that area, but are they thinking in that area? Because it's it's not very environmental friendly.
I think that is the E part of it, which is very the whole idea of you're going to move to electric vehicles and the performance of those and how much you have to charge and the life cycle costs of where you charge, right? Where you put your charging infrastructure in a way and where you're getting the energy for it that's charging. I think those are very much things that people do think about. I think if you ask, are they thinking enough about it, it's a different question, right? But it's certainly something that people care about. Yeah. Yes.
Sort of unrelated to data science, but are people thinking about how it's going to be for a human to
experience all this above them?
So, yes, so I think one of the privacy questions that I didn't talk about is the privacy question of, do I want somebody flying over my backyard to drop a package off to my neighbor, right? And I think there are some, yeah, so I think public perception is something that people definitely think about. I don't think that the projections that I showed on the number of flights actually take into account how annoyed people are going to get. One of the biggest complaints that people have about helicopters, like New York now has helicopter service where they do some of this, right? They're not eVTOLs, but they're more conventional helicopters, is noise. So I think if somebody came and said, I'm going to do this at these scales with conventional helicopters, it would not happen because the noise impacts are too high. I think with the smaller drones, I mean, you can kind of hear them. They're 100 feet up or a couple of 100 feet up. You can hear them. Yeah, so I think.
What about like looking at the clouds and making pictures of the clouds?
So that's a good question. So interestingly enough, if you look at like the environmental, the NEPA, the environmental concerns that people had about aviation or actually even power lines back in the 60s when people started caring about environmental impacts, it was entirely visual. I think since then, in the 50 years that passed, we realized there are worse things happening for the environment than the visual impact. But at some point, I mean, there is a question of when does the novelty wear off, and when does it become, intrusive? And again, if somebody drops a package in front of my house, do I get to keep it?
So hello. So I just had a concern about maybe I think you've addressed like sort of the application of this in like the private sector, but I was wondering about the public sector and whether you have any insight, especially concerning privacy, that would be helpful for legislative protection, or maybe avenues or aspects of this that maybe someone like that a legislator wouldn't think of that you might have insight to.
So one of the questions is, I think, especially with the privacy, there needs to be a way in which I can say, and the system or the operators can enforce that I do not want somebody flying over my backyard, right? So currently there are places all across the world, and certainly in the US, where you cannot have commercial flights, right? You have a no-fly zone, and you block that region off, and it's over a military base, let's say, and you do not allow it. You need now the ability at this scale for private individuals to actually say, we can't fly over this, and you also need the ability to actually enforce that. Right? I think it's one thing to say I don't want people to be able to publish that, but if they do, what is the enforcement, and who gets to, what happens afterwards if it's violated, right? So I think there's a huge regulatory question there. But there's also, I didn't talk about things like public use cases. And I think ultimately the social good, like it's not, there's doing this privately that matters, but then if you can reach places that you don't usually reach, or you can do things where you don't have the labor force to do, I think that is probably where the true benefit will come up, right? It's not going to be, the investments might be in the private sector, but certainly disaster response, and we have some work that we've just started with the Japanese Aerospace Exploration Agency on where do you put drone bases, because if you have a disaster, you need to be able to respond. And if you're doing search and rescue, search with a drone is something that you could do quickly and then use your helicopters for rescue, right? But first, again, if you think about it, you need to know where to go and pick up people, where you have to evacuate people from. And so being able to quickly respond to that, I think that kind of thing is probably, if you think about it, you want to address those use cases, right? That's where you get societal good out of this.
Thank you very, very much, Professor Balakrishnan.